Yeah, thank you for giving me the opportunity to present some of the results that were obtained mainly at during the postdoc at Harvard in this audience. And thank you all for joining. So the title of the presentation is Nonlinear Optical Diode Effect in a Magnetic Weyl Semimetal. Now, of course, the first question that comes to mind is what is a nonlinear optical diode effect? And diode effects in general are quite ubiquitous. Like the probably most well-known example is an electrical diode that conducts electricity well in one direction and blocks current in the opposite direction. So a diode effect, using this example of an electrical diode, is just a directional asymmetry of some material property. There are also these diode effects in the optical regime. For instance, one can create a linear optical diode if one wants to call it like that. It's more commonly known as non-reciprocal directional dichroism, where you have a directionally dependent absorption. So the sample transmits light in one direction better than in the opposite direction. And expanding on this idea, one can now also conceptualize a nonlinear optical diode effect, where a nonlinear optical process happens in the material. And in this case, for the purpose of this talk, this will be optical second harmonic generation, so a frequency doubling of light. So a nonlinear optical diode effect, or node as I will abbreviate it, is just a directionally dependent SAG intensity. So in one propagation direction, you have high intensity, in the opposite direction, you have a lower SHD yield from your sample. Now, if you look at how pronounced these optical effects are for the non-reciprocal directional dichroism, it's typically just a few percent change of the absorption coefficient of the material, which is more than enough to get us a measurable effect. But also, it's a kind of a narrow band effect, so that it primarily occurs near resonances in the material. For the nonlinear optical diode effect that has been observed before in magnetoelectric insulators, one can realize a near 100% change, meaning one has a finite second harmonic generation in one direction and almost no SHG response in the opposite direction. But also here, the bandwidth is restricted and it stays somewhat close to sharp electronic resonances. What I want to show you in this presentation is that if you consider a nonlinear optical diode effect in a magnetic Weyl semimetal, you can also achieve a near 100% change, directional change of SHG intensity, but you gain a broadband response due to the electronic band structure of the Weyl semimetal. So this is essentially the bottom line of this presentation. And if you remember nothing else, just remember that because of the electronic band structure of Weyl semimetals, you can get optical broadband responses. Okay, going a bit more into the details, why magnetic Weyl semimetals are interesting. So they are interesting because they show often intricate coupling effects between electronic and magnetic properties. So especially one can be in a situation where maybe the material is already a Weyl semimetal in the paramagnetic phase, has some Weyl nodes somewhere in the Brillouin zone, and then as one cools down, the magnetism emerges and changes the electronic band structure, which moves the Weyl points around in the Brillouin zone. But this is a kind of electromagnetic, magnetoelectric coupling. And this interplay between Weyl fermions and magnetism in general provides a relatively fertile ground to discover novel electromagnetic phenomena and magnetoelectric phenomena. A specific material that we'll be looking at in this presentation is serum aluminum silicide. It has a tetragonal crystal structure that is already non-central symmetric in the paramagnetic phase at high temperatures. At sufficiently low temperatures, below about 8 Kelvin, the cerium moments order in this weak ferromagnetic alternating fashion, which then also breaks time reversal symmetry. And it gives rise to 4 magnetic domain states with a net magnetization either along the positive or negative X direction or the positive or negative Y direction. At this situation where the crystal structure is always non-central symmetric, but additional symmetries are broken at low temperatures, is it's an ideal situation for nonlinear optical investigations, like second-harmonic generation, which is a process that is only allowed in non-central symmetric materials. And in general, second-harmonic generation is a process where two photons of frequency omega interact in the material and lead to the emission of one photon at frequency 2 omega, at twice the frequency. And this process is mediated by this nonlinear optical susceptibility tensor. The symmetry of the material defines which components are allowed here. Now, in our situation, we are already in the paramagnetic phase. The material is non-central symmetric. We are in a situation where there is a crystallographic contribution to these chi-tensor components that is invariant under time reversal symmetry. And because it's invariant, we call it I-type as a common terminology. And then at low temperature, when the magnetism emerges, the symmetry reduction leads to an emergence of additional chi-tensor components that are linearly proportional to the magnetization and that change under the time reversal operation. And because they change, we call them C-type. Now, in the experiment, we don't measure the susceptibility directly. We can only measure intensities, and you can already see what's happening is that you get interference between the crystallographic and the magnetic second-harmonic generation contributions. So you can imagine that maybe for some domains, this interference is constructive. For other domains, it's destructive. So you end up getting a magnetic domain contrast that can be useful to image magnetic domains. To check if this works, we built a setup where we shine light at an angle of 45 degrees onto our sample. We measure in reflection, filter out the fundamental light, and propagate the second harmonic light through some imaging system onto a CCD camera. The sample itself sits in a cryostat where the temperature can be controlled, and we have the opportunity to also apply a small magnetic field along the X or Y direction of our sample, which is sufficient to saturate the magnetization. Now, if we don't apply magnetic field and just look at what we get, we indeed find a pretty nice domain image where we can distinguish 4 brightness levels like almost white, almost black, light gray, dark gray. And by comparing the SHE intensity levels with the SHE intensity that we get in the field, in the magnetized state, we can identify that the white and black correspond to magnetization up and magnetization down domains, and light gray and dark gray correspond to magnetization pointing towards the right or left. So that's the positive or negative X direction. Okay, now this is just a magnetic contrast. Now we are actually interested in a nonlinear optical diode effect. So to check if we also get a diode effect, we reverse the beam path. We physically changed the setup and measured the SHG response in forward direction and in backward direction. And if there's a diode effect, then we might find different SHG intensities. Okay, how does this look? Well, if we measure in forward direction, and here I'm showing a polarizer plot. So we are measuring in gray and red, the S and P polarized SHG response, and we vary the polarization of the incident light pulse, the K-in. So there's a clear polarization dependence of the SHG response. Nice. Now, if you reverse the light propagation direction, we find a very different SHG response, a very different polarization dependence. And you can imagine, okay, if you just select one polarization component, say the one where we have here S polarized incident light, then in forward direction, you get a maximal SHG response. In the reverse direction, you get almost no SHG response. Okay, but also, we can also look at it a little bit differently in comparison to the non-reciprocal directional dichroism, the linear optical effect that I mentioned earlier, that is defined as a polarization independent change of absorption coefficient. We can also try to define something like a polarization independent SHG response, which we termed integrated SHG intensity. What we did there is essentially we removed the polarization analysis for the SHG response, simultaneously detecting S and P polarized SHG light, and we average over all incident polarizations. And then also we find that indeed in forward direction, we just get a higher integrated SHG intensity, and in the reverse direction, we get a lower SHG intensity. So there is clearly a diode effect. Now we can apply the opposite magnetic field and force a minus Y state with the magnetization pointing in the negative Y direction, and we see the opposite picture. Where then in the forward direction, we get the lower intensity, and in the backward direction, higher intensity. So essentially, by controlling the magnetization in the material, we can control the directionality of our diodes. That's something that you can rarely do with other diodes. Okay, we also noticed that in this case, reversing the light propagation direction and reversing the magnetization has the same effect on the polarization dependence. That is indeed consistent with the symmetry of our material, is not in general expected, but it happens in this case. Okay, now I want to emphasize this a little bit further. I want to talk about the symmetry of the nonlinear optical diode effect a little bit more. So ultimately, it's an interference effect. But it's separate, it's different from the magnetic domain contrast that I showed you in this domain image. So here, what gives rise to the contrast is interference between I-type and C-type SHG contributions. So contributions that are even and odd under time reversal symmetry. Also, the non-reciprocal SHG response, so that is the node that was previously observed in magnetoelectric insulators, is also an SHG response. So here one wants a contrast between K and minus K light propagation, where K is the wave vector of the light. So essentially you want to then interfere SHG contributions that are even and odd functions of K, which turns out to be even and odd functions with respect to spatial inversion symmetry. So also this is an interference phenomenon, but it's distinguished from the magnetic contrast by how you separate, which tensor components interfere. Well, what's the symmetry of the interfering tensor components? And now for the node that we observe in reflection, what relates the two propagation directions of the light is the mirror plane that goes vertically through this sample. So that means to observe a node in general, what one needs to achieve is one needs to have SHG tensor components that are even and odd under this mirror operation. So you see that it's again a different symmetry that defines the presence of the node with respect to non-reciprocal second harmonic generation or the magnetic contrast. If you want to systematically show this maybe in the form of a Venn diagram, one could plot something like this, where we have a pocket somehow representing all materials where a non-reciprocal SHG response can be expected. So where interference between even and odd tensor components with respect to spatial inversion is feasible. And it's one possible mechanism to realize a nonlinear optical diode effect in some materials, but there are other mechanisms. So this pocket is fully contained in all the materials that may show a nonlinear optical diode effect, where we need interference with respect to the mirror operation between even and odd tensor components. And both of these phenomena actually are independent from the magnetic contrast. So both of them can occur also without ever breaking time reversal symmetry. So this magnetic contrast where we interfere T even and T odd tensor components is again different. Our work sits here in the intersection. So we do not have non-reciprocal SHG in our system, but we do observe a node, and we do have time reversal symmetry breaking, which allows us to control the magnetism to control the directionality of the node by the magnetism, which is possible if you're in this pocket. Okay, and actually also all reports that I'm aware of non-reciprocal SHE sit in this pocket, although strictly speaking, it's not necessary to get non-reciprocal SHE only when you have also a time reversal symmetry breaking. Okay, now I showed you already that the diode effect can be controlled here with the direction of the magnetization. Of course, for applications, it would be even better if we could do this electrically. So you can imagine that maybe you want to pass a current through your material, and that flips the magnetization. And then by controlling the current, you can control the directionality of the diode effect. And it turns out that that actually works. In this case, we pass a current in X direction, and it switches the magnetization very clearly along the Y direction of our crystal. There's a very clear hysteresis in this picture. And because we do actually have a CCD camera, I can show you a little image, a little video how this works. So as the current is varied, you can see that. So sorry, I should explain. We pass a current along the X direction, so specifically between electrodes 2, 3, 4, which are by themselves shortcut, and 6, 7, 8. So current passes in this direction, back and forth, and we change the magnetization along the Y direction. So the bright domains are the ones with magnetization pointing up. And in this case, the dark areas are all other domains, but we did verify by looking at the polarization dependence that the dark areas are predominantly magnetization down domains. Okay, now a question that, sorry, and this process is very reproducible. It works for many cycles. We did not see any fatigue or anything like that. It's quite nice actually. Okay, a question that often occurs here is, okay, if you pass more than 100 milliamp through a millimeter-sized sample, aren't there heating effects? And indeed there are. So you can see this also here. If we go to larger negative currents, the SHG intensity decreases, and then it increases for a while as we reduce the current back to zero along this arm. And this is exactly because of heating effects. At this high current. We try to quantify this a little bit, or make sure that also here at the highest current we are still in the ferromagnetic state by mapping out the SHG intensity under a magnetic field as a function of current and temperature set point of the cryostat. And we see that indeed at 3 Kelvin, where we did most of our experiments, we are still in the ferromagnetically ordered phase, although the transition into the paramagnetic state is kind of close. So to overcome this and look a bit more carefully at the effect of temperature, we produced a mesoscopic, a miniaturized sample, basically, by focused ion beam milling. This red structure is the serum aluminum silicide sample that is sitting on gold electrodes and is contacted through these metal patches. And also in this structure, we can electrically control the magnetic state by passing a current of, in this case, then only 3 milliamps, because the structure is much smaller, the current density is much higher. There's no hysteresis, presumably due to some built-in strain or shape anisotropy of this structure that favors one magnetic state. But we see that with the 3 milliamp that we pass maximally in this experiment, we barely have any heating effect, meaning that at least heating is not relevant for the magnetic control, for the control of the magnetic state. Okay. Now, so far, I have shown you that there is a diode effect in this material, but so far also all experiments were done at one specific photon energy of 715 millieV incident photon energy. But I promised you that this would be a broadband effect. So of course, I'm going to show you some spectroscopic data, but very systematically vary the wavelength. And indeed, we find that we have a different SHG response in forward and in backward direction over a very wide spectral range. Actually, this is the whole range that we got that was experimentally accessible. And yes, well, yes. And also here we did the control experiment and reversed the magnetization, where we then find very similar spectra, but the order is changed. So suddenly, in the reverse direction, we have a high SHG response, and in the forward direction, there's always a lower SHG response. So indeed, we get this diode effect, which is essentially just the difference between those two curves over a spectrally very broad range, which is quite unusual. Excuse me, to quantify this a little bit more, we introduced a directional contrast, which is simply the difference over the sum of the measured SHG intensity between the two propagation directions in a well-defined magnetic state of the sample. And this contrast we mapped out as a function of laser polarization and photon energy, which then yields this rather nice looking figure. We notice here certain symmetries in this figure. So the picture is mirror symmetric around the 90-degree direction. The image is also cyclical, so in the sense that 0 degrees and 180 degrees are identical, and it would repeat again. So it's also mirror symmetric about the 0-degree direction. So this is the horizontal and the vertical axis of our sample, and it's exactly the mirror planes of our material. So this symmetry is expected. We also see that in the maximum we achieve a contrast of more than 97%, which, if I remember correctly, is about an 80-fold change of SHG intensity between forward and backward direction. And if we, well, more importantly, if we allow ourselves for each photon energy to choose the polarization such that we get the maximum contrast, we get this curve on the side. And we see that by adjusting the laser polarization accordingly, we can achieve a contrast of 72% over the whole experimentally accessible photon energy range. And now 70% may not sound like it's close to 100%, but it's still a 6-fold change in SHG intensity between forward and backward propagation. Now this is a very significant effect. And if we compare this again to previous reports in magnetoelectric insulators, there the bandwidth of this observed effect, of this observed diode effect, is typically less than 5 millieV at comparable photon energy ranges. So it's a much spectrally a much narrower response. To understand better why this is the case, we then got in touch with some theory collaborators who calculated the electronic band structure of the material. In the band structure, they indeed find that there are Weyl nodes in the calculations in the material. Now, if you show the band structure along this path between high symmetry points, you typically miss the Weyl points. So this path is not expected to go through the Weyl points. That's why the rough locations where Weyl points would be is only shaded here. And then in DFT, you can also calculate the SHG response of the material. And essentially, the SHG intensity that would come out can be expressed as a Brane zone integral over some quantity that we label here kappa, absolute value squared. And kappa is essentially something like a K-space resolved nonlinear optical susceptibility. So by looking at the absolute value of kappa, we can get an impression where are the relevant electronic states that contribute to our SHG response. And there we can distinguish two qualitatively different scenarios. So there are some states, like this one over here, close to the gamma point, where we get a large response for certain photon energies, but a much lower response or almost absent response for different energies. So this is a typical resonance behavior, if you like, that where if you have a matching photon energy, you get a response. Otherwise, you don't get a response. And this is explained because the bands at this location are roughly flat, approximately, or relatively flat. And then there are a whole lot of other contributions to this kappa at different points in the Brillouin zone. And those typically occur in locations where the bands are dispersive, like along these points. So what happens there is that as we change the photon energy, yes, the position in K-space where the transition happens changes, it moves a little bit. But for all photon energies, there always is a transition that gives rise to some SHG response, and hence also to a diode effect with comparable magnitudes in general. So this is qualitatively different, and this is from a magnetoelectric insulator where you would predominantly get this resonant responses, and this is microscopically the origin of our broadband response. We looked at this a little bit more carefully because this is just a line through a line cut through the Brillouin zone, which is in itself actually a three-dimensional object. Now, imaging it in 3 dimensions is difficult, but we can at least look at a cut through the Brillouin zone at a certain value of kz. So this is the kx, ky plane. Specifically, we chose the plane that contains some of the Weyl points that are marked as, the locations are marked as dots here. And color-coded are the states that contribute to the SHG response. And the more intense the color, the higher the contribution. We can see that around the Weyl points are 2 lines. They're hugged by 2 lines, which we can understand. So the inner line is the line where the transition is resonant at the fundamental frequency at h bar omega. The outer line is the line where the transition is resonant with 2 omega. And now if we vary the photon energy, we can see that the lines, with increasing photon energy, the lines move away from the Weyl points. But this is exactly due to the linearly dispersive nature of the electronic bands near the Weyl points. And one can even check that as the relevant states move roughly, the distance between the contributing states and the Weyl points increases roughly linearly with photon energy. Okay. So that confirms again that the linearly dispersive bands that naturally occur in Weyl semimetals are the origin of the nonlinear optical broadband response that we observe in the experiment. Okay, before I summarize my presentation, I would like to acknowledge the people who contributed to that work. So most of the experiments were done during my postdoctoral time at Harvard University in the group of Tzschaschel. The density functional theory calculations were done by Katie Law at Hong Kong University and his students. The microscopic device, a mesoscopic device, the focused ion beam MILT device, was prepared in the group of Philip Moll at the Max Planck Institute in Hamburg. And samples were provided from the groups in Boston College, from Faisal Tafti, and from the Chinese Academy of Sciences in the group of Fuchang Wang. And with that, I'd like to summarize. In this presentation, I presented you a nonlinear optical diode effect as a nonlinear optical response that one can observe. And we verified that it does indeed exist. We showed you that we demonstrated that we can electrically control the diode effect by passing a current through the material. And most importantly, we observed a broad band response in this magnetic Weyl semimetal serum aluminum silicide. And supported by DFT calculations, we identified the dispersive bands that naturally occur in this material as an origin of this broadband response. And I also want to mention that this is one of the first observations of a nonlinear optical response due to magnetism in any topological material. And with that, I'd like to thank you for your attention.